I'm Aya from the Ministry of Education, Culture, Sports, Science, and Technology, MEXT. With the aim of further advancing climate change studies and utilizing the results for society's benefit, MEXT Japan has launched the program for the advanced studies of climate change projection called CENTAN this year to address the need to elucidate climate change mechanisms, reduce uncertainty of climate change projections, increase the sophistication of climate change projection models, assess climate change impact, and develop sophisticated climate change projection datasets. Also, the Ministry of Environment has promoted the S28 program with a focus on GHG budget. Some of the speakers today are leaders of these programs who works closely with each other and colleagues from the international community as represented by the invited speaker as the program. As you know, the writing and approval process for the IPCC AR6 is underway and expected to be completed in early 2023. The collection of findings from the previously mentioned programs and other related research outcomes has contributed to this IPCC assessment report and serves multiple policy objectives, including adaptation, mitigation, investigation, and research on climate change impacts. Japan's GHG observation satellite has undertaken the world first mission dedicated to measuring CO2 and methane emissions, thereby helping improve the accuracy of GHG inventories. In addition to observing GHG emissions from space, Japan has observed global forests as well as land cover and changes from more than 25 years using synthetic aperture radar. The collected information helps us understand the emissions and removal of land sector. Furthermore, Japan has research vessels that provide high precision oceanic observation data, including cryospheric data to understand global oceanic changes. Using these precise and accurate data, Japan promotes research and international cooperation in support of better decision making. To foster the accumulation and use of big data in the global environment, including GHG observation and projection information, the Data Integration and Analysis System, DIAS, and AP-PLAT has been established, which collects and store Earth observation big data, analyzes these data in combination with socioeconomic information, converts the data into information that is useful for crisis management with respect to global scale environmental disaster and other threats, and make this information available in Japan and overseas. Japan reaffirmed the importance of Earth observation, including satellite, atmospheric, ocean, and land observation, and foundational scientific research has produced accurate and timely climate models to strengthen national and international data-driven action regarding climate and biodiversity challenges. Japan is pleased to contribute further to this area of research and systematic observation. This seminar will introduce scope for near future projection of GHG levels and climate change impact assessment using Earth system models. Thank you for your kind attention.
So we will now enter the technical session, and our first presenter is Dr. Michio Kawamiya, and he will talk about the Earth system modeling for gaining comprehensive understanding of global change. Oh, why is Zoom should share? So, Kawamiya-san, please.
Good afternoon. Am I loud enough? Okay. Yeah. Okay. Thanks. I'm Michio Kawamiya from JAMSTEC, and as a first speaker, I will be talking about climate modeling, and I'm involved in the national projects shown in the bottom of the slide. The two national projects. One is Sentan, and the other is some some part of the symbol mark is cut off, but it's called S28, and I'm mainly talking about the Sentan project or its predecessor, Togo project. It's a national project for climate, global climate modeling, and I understand the audience is a kind of mixture of people working on climate change from various different aspects. So not everyone is very familiar with the climate model. So I'm showing this panel just to give you an idea what it does. And it's a projection for global warming, and reddish colors shows the warmer place, and blue colder place, relative to 19th century. And the number in the top shows the year, and around the end of this century, the Earth is covered by reddish color. Although it's under the scenario with the highest emission, which is now more or less unrealistic. But this is something that we can avoid by implementing Paris Agreement. And nowadays, recent climate models tend to have more components like ecosystem on land and in the ocean, as is shown in this figure. And moreover, recently we are trying to incorporate even the human activities like agriculture and land use and other components. And with this another information, I'm showing the outputs of such climate model with the ecosystem, which is often termed as Earth system model. So this shows annual cycle of CO2 concentration in the atmosphere, and the lower panel shows the absorption or release of CO2 by terrestrial vegetation or the ocean. So the number here shows the date. So now it's winter, so you have more CO2 in the northern hemisphere because you have less photosynthesis on land. But then as time goes by, and then now it's more or less summer, and the land photosynthesis become vigorous, and you have less CO2 concentration because it absorbs CO2. And then well, still it's summer, but the reddish color can be seen around the mid-latitude because the anthropogenic emission is very high in that region. And now it's becoming winter, and you have more or less the original distribution of CO2, where the CO2 concentration is higher in the northern hemisphere, reflecting the higher emission, anthropogenic emission of CO2 because of the population. Okay, and first, one of the most prominent and well-known results that have been achieved by such Earth system models is this figure showing the very simple relationship between accumulated CO2 emission on the horizontal axis and the transient temperature rise. As you can see, the model shows that the more you emit, more warmer you get. It's kind of something that you can expect, but it shows we can be sure that so the things are not like this. It doesn't saturate, or things are not like this. There's no runaway effect or something like that. And based on the this kind of relationship, which was shown by is a system model, you can easily estimate how much you can emit to be consistent with the set target of global warming, like 1.5 degrees or something like that. So, so if your target is 1.5 degrees, you can emit this amount of CO2 as a total. And this table is from IPCC's report, the latest one. And this is rather complicated, so sorry, but you read this table something like as to achieve 1.5 degrees target. If you limit the accumulated CO2 emission to 500 in this unit, then the probability to achieve the target is 50%. Okay. So if you emit less, like here, then the probability is, of course, higher. And but not everyone have a sense of how much is this, 500 or 300 in this unit. But for example, current emission, yearly emission over the integrated all over the world is 40 gigaton CO2 in this in the same unit. So it's about 10 years or something like that. So you can realize that how emergent it is. And this kind of information is quite, I think it's quite important for the coming global stocktake, which is a 5-yearly consultation for re-examining emission cut targets under the framework of UNFCCC. And other than, well, this kind of upper limit of carbon emission is often called carbon budget. And the carbon budget is one of the most important elements, I think, for as a scientific input for global stocktake. And other than the carbon budget emission, there are some other aspects that you can that system modeling can contribute to mitigation policy. And this, I think this is a good example where you estimate this kind of side effect of introducing bioenergy. And introducing bioenergy is, of course, good for mitigating climate change, but it also has a side effect because to produce bioenergy, you need more cropland, and well, cropland for bioenergy is often not really good at accumulating carbon into the soil. And this study this study from the national project that I mentioned estimates that kind of side effect, and it actually shows that the place where you have a vigorous bioenergy production, you have less carbon sequestration or absorption. So, well, I'm not saying that bioenergy production is bad because of this, but you have to, what the study is saying that you have to be careful but, on selecting the place for bioenergy production. And furthermore, we are trying to incorporate other human activities like land use and irrigation and other agriculture activities. And well, this is this figure shows the examples of such efforts. And well, the image is not good. And sorry, and I'm running out of time, so I'll stop here. But I just suffice it say that you can estimate the impact of climate change on food like this. So you have less food production because of the high temperature change and higher temperature, and you can estimate the total effect of mitigation policies like this. And I hope I convinced you that our system models are becoming a very powerful tool to understand the total effect of climate mitigation policy. And I'll stop here and thank for your attention.
Thank you, Kawamiya-san. And our next speaker will be Akihiko Ito. And his talk will be on another project we have in Japan. Greenhouse gas monitoring with Japanese observational facility and model. So, Ito-san.
Thank you. Hello, everyone. Can you hear me? My name is Akihiko Ito, researcher of National Institute for Environmental Studies. I'm happy to be here because last year we have a similar seminar, but today I can show our progress, recent progress in our project called S28 project. As Kawamiya-san said, the global stock take is ongoing, and we are now the second technical assessment or technical dialogue stage of global stock take. So this global stock take is very important milestone for the accomplishment of Paris Agreement. For every 5 years, the researchers should provide the most reliable, the best available science greenhouse gas budget to the community. So this is important to make the nationally determined contribution NDC more ambitious. So our program is very important to make contribution to this community by the Japanese activities. In our project, we have two approaches, so-called top-down approach and bottom-up approach. And the top-down approach starts from the atmospheric observation of greenhouse gases. So by using the atmospheric inversion model, we can estimate the surface budget of greenhouse gas budget exchange. This is a top-down approach. This is very ambitious to cover the global scale, but it is sometimes expensive. On the other hand, bottom-up approach starts from the individual source of carbon greenhouse gas emissions, and sometimes includes the natural sector carbon uptake. So this approach uses emission inventories, biogeochemical models, and sometimes satellite products such as fire. So by comparing with the top-down result and the bottom-up result, we can get more reliable, more credible budget of greenhouse gases. This is the basic concept of our project. So our S28 project, funded by the Ministry of Environment, starts from last year, and we have this is a three-year program, and this project consists of 3 themes: top-down theme, bottom-up theme, and a system model themes, as presented by Kawamiya-san. And this project estimates the greenhouse gas budget at multiple scales, from urban scale, regional scale to the global scales. And by comparing mutually, we get the uncertainty range or a credible range of our budget. So finally, we provide our result to the Paris Agreement global stocktake. This is This is the example of our bottom-up approach. We use anthropogenic emission by Edgar and biochemical model called BIGIT to estimate the natural sector emissions. So by combining these results, we get a global map of CO2, methane, and nitrous oxide budget for each year. And we are now updating this approach by using recent data. This approach covers 2000 to from 2000 to 2018, but now we are covering the more recent years until 2021. And this is a result by Chiba University researchers. We are using a machine learning approach to do the data model fusion. We use flux measurement data at the field, and by using a machine learning approach, such as support vector regression or random forest, to extrapolate the spatial coverage. So we get a very good result in compared with the previous studies. And also we are using the geostationary satellite data to estimate the diurnal change of vegetation activities. This is very ambitious satellite data use to improve the natural sector CO2 uptake. Top-down approach is very complicated, but because it includes various kinds of observations and modeling. Mainly in our institute NIES, which covers the Asia Pacific region widely, and we have many ground stations and ship measurement and aircraft measurement, and also we have a satellite measurement by COSAT. And this picture shows some example of our measurements, such as Tokyo Sky Tree metropolitan area, Tokyo area observation to capture the human emissions. And we also show the result of aircraft measurement and some isotopic measurement in India or some maritime measurement in Hateruma Island. This kind of observation captures short-term variations of greenhouse gas budget, such as the impact of COVID-19. These data are available from our global environmental research database. And we have this kind of atmospheric inversion data model called NICAM. This model allows us to estimate the surface CO2 budget and methane budget at very high resolution. So this is an example of the surface inversion result, and some seasonal change are well captured by the model. And also we have another atmospheric inversion model called Miroku ACTM, developed by Patrasan. This model starts from prior flux data, and by fusing by using the various kinds of atmospheric data, this model provides a posterior flux after the optimization of the errors. This is an example of his result. This CO2 and methane and nitrous oxide inversion result for major regions. So this approach allows us to estimate the decadal change or regional variability or distribution of the greenhouse gas budget. And this result made a very good contribution to the recent IPCC AR6 reports. And after then, these results are combined into a short report called the Bulletin of Greenhouse Gas Budget. We include both top-down and bottom-up approach result in this report. And we submitted this report to the UNFCCC Global Stocktake Portal in this March. To deliver our result to a wide range of stakeholders, we have periodically this kind of event. This is the example of COP25 and COP26. And we are happy to have a seminar at that COP27 here. And this is the concluding remarks. I don't repeat my summary. And our most important take-home message is that further data accumulation and model analysis clearly through international collaboration for coordination of modeling and observation required to improve accuracy. That's all. Thank you very much.
Okay, thank you very much, Ito-san. And now we will go to our next speaker, who is Kevin Bowman from NASA. And he will talk about the greenhouse gas monitoring from the space, prospects and challenges. And here you go, Kevin. The floor is yours. Thank you.
Can you hear me okay? Okay, sounds good. The fundamental question that COP27 has to address is, can we control our future? For the last 150 years, we have adjusted this climate trajectory in a direction that's unprecedented in our human history. We started in this pre-industrial point, and over time, we have moved to a location that's increasingly inhospitable to our existence. The question is, can we go back? Can we go back to a time frame closer to the pre-industrial past? Do we have control to reach a predictable outcome? Will it look like the future there? Or will it look like another future, increasingly inhospitable? The necessary condition to answer this question is, can we observe and identify key aspects of the Earth system? What do those look like? First, COP27 is focused principally upon the left side. What does mitigation care about? The reductions of fossil fuel emissions. But the climate does not directly respond to emissions. It responds to concentrations. And that is very important because concentrations are mediated by feedbacks and the natural cycle. Climate is changing right now, and it modulates the amount of CO2 and the amount of methane that is in the atmosphere. And it's precisely those concentrations that the Earth system responds to that leads to what we all care about: water availability, food security, droughts, etc. In order for us to address whether or not we can return, we have to be able to observe both what mitigation cares about and what the climate cares about. But they exist on two different scales. This is an unmistakable signature from space of human activity and our dominance on this planet. But one thing I want you to notice is the fine scale features that we see from night lights. They can be both small in nature, very pointed, as well as expanded. The kind of observations you need to understand the emissions are different. For example, there's an instrument called imaging radiometers or spectroradiometers. They can have spatial resolutions of 30 meters, and they're now being used to identify and quantify from space carbon dioxide emissions. This is two examples, one from Poland and the other one from South Korea. The one from Poland that you can't read whatsoever because of the, it's below the screen, is about 3,000 tons per hour. And if you look across at the top is showing you the total accumulation of coal-fired plants and how much emissions they have. We can see now these very high-level emitters in places like Poland and South Korea. New imaging spectrometers are being put to play. We'll be hearing more about the EMIT instrument from NASA tomorrow at the US Center. I encourage you to take a look there to move that number to the left so that we can see increasingly smaller emission sources that allow us to have a complete assessment of all of the emissions from these fixed point sources. But that's not the only scale. What can we learn about larger scales about the anthropogenic footprint? One of the important aspects of carbon dioxide emissions is that they are co-emitted with air quality pollutants. But the way in which they evolve of air pollutants and carbon emissions depends on the fundamental technology and economy that you're in. So if you look in the top left graph, you'll see that there's 3 quadrants. The first one is an activity when emissions of air pollutants and emissions of carbon are going up at the same time. And that's indeed reflective of a place like India, where you can see both from space using air quality emissions, those increases. China, on the other hand, has turned the corner, where now their emissions and air pollutants are reducing, but the carbon is still increasing. And that's the second quadrant. This is something known as the environmental Kuznets curve. And thirdly, you have when you beginning to see reductions in carbon and air quality, that is Q3, and that's what you're seeing with the United States. By using air quality measurements, we can predict the evolution of carbon with about 2 to 3% accuracy with a 1-year lag. This is the kind of information that we need in order to address things like the global stocktake. What about nature? Nature has its own say about how carbon dioxide is changing. And this is an example of the atmospheric fingerprints of the carbon cycle. What you're seeing in red is increases in CO2 relative to a mean, and blue are decreases in CO2 relative to the mean, reflective of uptake of carbon or the release of carbon. This time frame, you can see furthermore, as we go further in time, you see more red in the northern hemisphere relative to the tropics or the southern hemisphere. That is the imprint of fossil fuel emissions beginning to imprint itself upon the atmospheric variability of CO2. We use this information and the variations in that with another type of satellite. For example, the OCO2 sounder, hyperspectral sounder, very similar to the Japanese GOSAT instrument. This allows us to have the kind of global coverage that you need to capture those variations in atmospheric signals. And we use those with something called inverse models. Ito-san talked about those in more detail in the previous message, in the previous talk. And with that, this allows us to now make estimates of top-down estimates of carbon. This is work being led at the CIOS, Committee on Earth Observing Satellites. This is a pilot project. And what's powerful about these measurements is they provide the integrated impacts of both human and natural drivers of the CO2 growth rate, of the net carbon balance for many different countries. And what's also important about these kinds of data is that it can provide information that is global, transparent, and timely. This can play an important role in the global stocktake. Indeed, we see from the work at Deng et al. That a lot of places have not reported their emissions for many years. Indeed, 52 countries have not reported their emissions in the last 10 years. This is going to be challenging if you wish to understand or estimate what's happening in the last 5. But here we have estimates now. So for example, on the top right, you're looking at the US total net carbon balance, slightly more uptake relative to the reported emissions. But if you look in the bottom right, this is Brazil. And this is Brazil not reporting it since since 2016, right at the point of a major El Nino. And you can see several factors of difference in the amount of emissions, net carbon emissions coming from Brazil than what has been reported. This has to be accounted for if we want to understand the drivers of CO2 growth and ultimately the impacts for climate. Now, that having knowledge timely is extremely important because, again, nature is putting its own say, its own imprint. What you're looking at here is the role of biomass burning in Australia. This is carbon monoxide measurements made from the European TROPE-OMI satellite as well as the US CRIS satellite of carbon monoxide. And you can see that atmospheric signature. But as we go into 2021, you can see the massive increases in carbon monoxide. When you convert this to carbon dioxide, we get an estimate of 2020 of between 100 and 200 teragrams of carbon. That is equivalent to the fossil fuel emissions of Australia over the entire year. If you're thinking about a 5-year stock take, you just lost 20% of your time. Now, maybe it might be decided that that is not for Australia to bear. But if it's not for Australia to bear, someone has to bear it because it's now sitting in the atmosphere. This is the kind of information that satellite data can bring to the table. Lastly, in order for us to be able to fully understand the carbon budget, we need a greenhouse gas information system that can resolve the canonical blind man and the elephant problem of only being able to see pieces of the picture. This is reflected in the recent national academies, US national academies, showing how you need to have atmospheric data, activity data, and increasingly non-traditional data as provided by folks like the Climate Change to be able to pull this information together. And lastly, just to echo Miyamaki-san, we have to understand it in the context of the full Earth system, not only the role of the carbon cycle, but the role of temperature, the drought, water and energy cycles. And with that, I just want to indicate again that I think satellite data has a crucial role for global stock take. It's going to require public international effort. And this constellation of opportunities, satellites listed below, can play an important resource in understanding how the carbon balance is changing and how we need to mitigate it to move forward. Thank you very much for your time.
Kevin, fantastic. And so we move on to the next speaker, which will be online, because Pep could not come here. And many of you know Pep. And yeah, so screen sharing stopped. And but Pep played the instrumental role. Yeah. Is it gone? Yes. Oh yeah, Pep is showing it on from the distance. Sorry, I should not have shown it. Yeah, Pep, please go ahead.
Very good. Thank you so much for the opportunity. And the talk kind of comes very nicely after all the various talks we heard so far. This is really a high level of key messages to make sure that, you know, we really keep in mind as we think about these net zero emissions. And let me just begin, you know, it has been said already, but, you know, we're trying to bring the carbon cycle back to into stability. And of course, the stability that results into an atmosphere that no longer grows with CO2 concentrations. In the center, you see the red, which is the human perturbation. But I think what I want to show you is what's very obvious, but it's very important to understand, is that the carbon cycle and the net balance in the atmosphere, which is what we ultimately want to understand, it goes along with these humongous fluxes from you know, nature. Let me just get the laser. So much bigger than anything that humans are doing. Not only that the anthropogenic emissions actually are influencing those natural fluxes in ways that, again, they're even bigger than the fluxes themselves that they originated those impacts. We're trying to bring all these systems, you know, back into balance. And we have to understand not just, of course, all the emissions anthropogenic activities, you know, lead to, but how these interact with these humongous fluxes, which may actually change into the future and I'll show you some really interesting work. Most of what I'm going to show is from the last IPCC report that we have contributed. Many of you have contributed, and some of the global carbon project work that we do globally. There's no better way to show, how important what I'm talking about is in the context of the atmospheric CO2 concentration than this waterfall figure. We started in 1850 with 286.
Sorry, Pep, if you can hear us, is some problem with the technical issues here, and your screen is frozen. Yeah. Pep, I think your presentation went out of the screen, so yes, and it stopped. Could you please try it again? Pep, can you hear us?
Maybe he's off the panelist list. So then, yeah, he's reconnecting, I guess.
Yes, you are speaking, but Pep, I think he's got disconnected. Yes. I don't see Pep on the screen. So Workers next talk. Yeah. Or just so Pep's slide, here you can show it. You can show the Pep slide for 5 minutes and then few minutes, and you can show Pep's slide here. So I think we don't see Pep coming in. So you can see his slide. I don't think you can talk, but you can slow him. Okay. I'm just trying to see if Pep is come back. I don't explain, but just finish his slides. So
What are the, maybe you can switch.
yeah, we'll switch. Yeah,
Right now.
yeah. Yeah, next step. Yes. Yeah. So yeah, let's move on to the next speaker because we lost Pep's connection, and our final speaker will be Sobakar Dhakal, and he will tell us about in the many mitigation options, because he also he participated as a lead author in AR6. So we expect, yes, we expect to know what is their summary. And Sobakar, please deliver your talk, and the floor is yours.
A very good afternoon to all of you. First of all, thank you to our JAMSTEC colleagues and organizers for inviting to this event. What I'd like to do this afternoon is to share with you some perspective, essentially coming from AR6, especially the chapter of emission trends and drivers, which is chapter 2 in mitigation report, of which I was coordinating lead author. And also some of my own perspective. I think Kevin really started with discussion about the mitigation challenges, and also the fact that what Earth cares is CO2 concentration, not the emission. But let me try to focus a bit on the emission side of the discussions that largely coming out from the IPCC AR6 mitigation reports, chapter 2. So what I'd like to do is to share with you some of the emission challenges, and also not only challenges, but also some of the emerging opportunities and few critical areas where I see very important as we go along. For that, a better cooperation within Asia and also outside Asia is very, very fundamental. I think this is not, this is very well used figure that we are not in track to meet a 1.5 degree, path to the warming to 1.5 degree. And if you look at some of the historical emission trajectory, and also how much emission budget we have remaining in order to stay to the limiting the warming to 1.5 degree, as you can see that we really don't have much space there. Hardly about 500 billion ton of CO2 equivalent more or less remain for 1.5 degree, maybe around 1200 gigaton of CO2 equivalent remain for 2 degrees Celsius. So what I'm trying to say here is that mitigation challenge and the space what we have is quite limited. Now, if you look at the relatively shorter term, let's say 2030, IPCC report have said that we have to reduce greenhouse gas emission by maybe around 43% by 2030 in the optimal pathways, and also we should very soon start to peaking, and then we have to come down very, very quickly. Now that already puts us into the very, very tight time frame, and in the little bit more longer time frame of 2050, we are talking about the net zero CO2 emission in very early 2050. So given that challenge what we have in order to move to the future, now if you reflect back what we are doing, what we did last couple of years, last few decades, at least from 1990, we started discussing about climate change quite actively globally. You see that our past trend is not very good trend. We emit, according to IPCC, our benchmark year was 2019, 59 billion ton of CO2 equivalent, greenhouse gas emission we emitted. Not only that, but in recent years, the amount of the emission, what we are emitting in the decadal average is a very, very highest in our recorded history. Not only that, but also some gases are rising very rapidly, particularly if you look at the F gases. You mean the green figure on down on your right, you can see that F gases is rising very rapidly, but of course, in terms of total emission, total amount, that is still less. But also, if you look at some of our trends, the energy systems and the industry, these are the very, very important emission sectors. But again, out of that 34% of the energy system emission, which also composed of electricity and heat. If we allocate that particular emission to industry and the building, then you see a little bit different trajectory where the role of industry sector becomes much higher from 24 to 34%, and role for the building sector becomes 10% higher from 6% to 16%. So given the challenge that what we have and how much emission space we have in order to maintain to 1.5 degree, and also what trend we have, we are not in very, very good situation. And if you look at historically again, which part of the world has been, emitting rapidly, and you see that the Eastern Asia is in very much limelight there, where the share of the Eastern Asia has become quite big, 27%. Back in 1990, it was only 13%. Of course, in some regions, the share has declined, especially in the Europe and North America, but also Southeast Asia, South Asia, and also Africa. That emission share is rising. So again, some of the regions where there is a lot of needs for development, also in quite a hotspot here, because the emission trends has been increasing there. Of course, if you look at emission trend, as you know that there are a lot of different perspectives in emission. If you look from purely growth rate perspective in last decade, maybe country like Vietnam, Indonesia, Turkey, Pakistan, they might look very, very big percentage growth in last one decade. But if you look at the absolute emission change, the China, India, Indonesia, Vietnam tops the world. But again, if you look from per capita emission, again, you see a different picture. But in totality, you can see that the role of Asia and the role of Oceania becomes very, very important. And this is where a lot of challenge we have to confront you with. Now, in that context, given the limited time what we have, I like to suggest that there are 6 areas which are very, very important in this discussion, particularly moving forward. The first important area is the harnessing sectoral mitigation potential. Now, what I mean by that is that, if you look at the recent IPCC report, which we published from mitigation side, there is an estimation that almost half of the emission by 2030 can be reduced by available options. And these options lie in different sectors: industry, energy, land use, urban, building, transport, and also the demand and services. But of course, these won't be free. And for that, the cost of about $100 per ton of carbon, up to that cost might be imposed there. But this gives us at least some idea that we have lots of sectoral contribution, and harnessing this sectoral mitigation potential is very, very important. Now, also the second important observation is that there are several countries, at least 18 countries, have sustained production-based greenhouse gas emission and also consumption-based CO2 emission reduction for longer than 10 years. Now, which basically means that how to basically scale up, how to basically deepen this reduction trend, and how to expand that to the other countries. That is where I think our thrust could be there. But at least this is some positive news that what we can move forward. And also, economically speaking, there are lots of countries where some decoupling of the emission trends from the growth trend has happened, either in absolute term or some relative. These are some of the good signs, but that doesn't mean that this is enough. And also, a lot of promising direction has come from some of the technological front, especially scaling up of several emerging technology. If you look at the case for photovoltaics, onshore wind, offshore wind, concentrated solar power, or battery, you see that the unit costs have declined quite significantly over last few decades, and at the same time, the deployment of some of the technology has improved. So how can we scale up this rapidly emerging technology is something very, very important. And also, IPCC report also have shown that some of the granular technology learns very fast. and at the adoption rate become faster, the learning rate also becoming faster. So we do have a lot of prospects from technology, but how to scale up technology, how to make it happen is very important. So the fourth point I would like to also highlight in this discussion is that there is an evidence of the increased climate action. Many countries have imposed carbon pricing, carbon tax, or the emission trading system. In many countries, there are direct climate laws focused primarily on greenhouse gas emission reduction. And also there are a lot of estimations exist on how much emission has been reduced by the use of the economic and regulatory instruments. So at least we are moving into the positive direction, but of course that is not enough. So this we should not forget, but then that is quite an interesting trend. And also the fifth point I would like to highlight in this discussion is the role of so-called lock-in of the emission in the fossil-based energy infrastructure. What I mean here is that, if you see the figure here, we have existing fossil fuel infrastructure and we have a planned fossil fuel infrastructure. Now, these are, we could call it already locked in emission or some kind of committed emission, which is already in our infrastructure. We have to stop this emission. If not, we keep on continuing this emission. So if you look at some of these numbers, you see that almost 668 gigaton of CO2 has already been logged in the existing fossil fuel infrastructure. Now, how to unlock that, how to release that, unlocking to release that, I think this is where is very important. So the last point also, I was trying to outline 6 different important areas is the role of cities. In 2015, role of cities in the global emission was around 62% estimated. By 2020, over 2/3 of the global emission is coming from cities. So how we can make city play more important role, because city is a place where a lot of different sectors and a lot of actions come together. This is very important, especially this is very important for Asia, because the future of urbanization, Asia has a very strong role to play. And also there is a lot of opportunities in order to make the urbanization correct and also to make city more efficient. So let me stop, in the interest of time, saying that these 6 different areas where we can still do a lot of work, given a bit of a pessimistic scenario of our past emission trend, and also very challenging time for the future in order to limit within the available emission budget. But still we have a lot more work to do. And in that front, the Asia and the Oceania and also rest of the world, we have to have better cooperation. And this is my call for better cooperation for working together. Thank you.
Thank you, Sobakar, very much. And it has been very nice session so far. And then I would like to have a round of applause for all speakers. Thank you very much. And now we'll be moving on to the, just to mention, PEP is back to the Zoom, but I think the lack of time, so we'll just move on to the panel discussion. PEP, hope that is okay with you. And on the panel discussion, 2 of our scientists will be joining from remotely, and 2 more will be joining remotely. So one from NIES, Ito Institute in Tsukuba, and one more from my institute, which is Kanayasan. And so but he'll be joining from Seoul. And probably we just need a self-introduction from Saigure-san and Kanayasan by just half a minute or something. And then I would request Kevin and Sobakar and Kawamiya-san to take over to the dais and use the opportunity to have the panel discussions. And we will be also open to questions from the audience. So
now you should
your name is called.
you also sit down in the front of the audience. No? Yeah. Or Kanaya-san and Sayu-san, have you finished your self-introduction? Not yet. Yeah. Okay. So we are entering the panel discussion, but we have two online panelists who are not speakers. So it would be nice, I think, to have them self-introduced. So may I start with Saigusa-san and then Kanaya-san. Ladies first.
Okay. Good afternoon. My name is Nobuko Saigusa. I'm working for National Institute for Environmental Studies. I'm studying on climate change and greenhouse gases. Thank you very much.
Yes, thank you very much. This is Yugo Kanaya from JAMSTEC, the same institution of Patra-san here. And I have been an air pollution scientist and have worked on as the IPCC 6 SFCF chapter as a review editor. And we study the CO2 together with SFCFs, including the GW satellite upcoming missions. Thanks.
And maybe Patra-san.
You all know me already. I think that I did the chairing of the first session. My name is Pravir Patra. I work for JAMSTEC, and I and Kawamiya-san are organizing this session. And it's very nice to work with all the people who are on the dais or who are on the Zoom. We had a lot of background work to prepare this. I hope you are enjoying it and we'll enjoy the next. Thank you very much.
Okay, and thank you, Patra, for organizing this. And this is his initiative, and I'm just helping him. And we are entering the panel discussion, and I wanted to have questions online, but there are not so many. So first, we should open the floor for questions. And if there are any questions from the audience on site, we'd like to have one. Or don't be shy. Speak up. Don't be like Japanese. And you're laughing, meaning that you have something to say. No. Oh. Okay. Please go ahead. The guy with the jacket.
Hi, good afternoon, everyone. Clément Albergel from the European Space Agency. It was very nice to see all your talks. Sorry, Pep, we could not see more of yours. I have a question to you. In your talk, you mentioned Asia and Oceania, but we are facing here a global issue. What do you think is still missing so we can really have a global integrated observing system for greenhouse gas measurement? Thank you.
Thank you. Can you hear me? Thank you for your question. In comparison with Europe and North America, the Asia-Oceania region has doesn't have a systematic observational system. So we don't have a good network of observational of field measurement and satellite measurement. We have now satellite measurement, but we don't have a systematic network of observation, and we don't have a big money. We don't have a good facility, so we need to maintain our existing facilities, and we should expand our facility to cover the Asia Pacific region. Yeah, thank you.
Next, the person next to the guy who asked.
Well, Frank Martin Seifert as well, European Space Agency, and my question was going a bit in the same direction. I see the reasoning for concentrating on the Asian Pacific region with the growth of population, the growth of the cities, but really I can only emphasize what my colleague said before. We need the international cooperation. We need to bring these efforts, regional efforts together to a true global observation system. And I think we saw the presentation from the US side, from I know about Europe. We are ready to work together and to come to bring our scientific forces together to come towards a global observing system. The problem is global. Only the solution we can find can only be found on a global level.
Maybe it's a question to Kevin, I guess. And
It was
maybe,
I don't know if it was a question, I think it was a comment. But one thing I would add is that there was mentioned briefly about the role of the JEMS satellite from Korea is now providing unprecedented NO2 concentration information over Asia. I would contend, not being from an Asian country, we need an equivalent geostationary sounder of carbon dioxide over Asia and an integrated system between different countries that can report, can estimate, just so we heard from our colleagues, they're trying to estimate a multi-scale carbon budget. We all need to agree on what that looks like how to report it. The US, with our assets, with Europe, with the Copernicus program, with CO2M and COCO2, we need to lay all those estimates out, lay them next to each other, and then learn to resolve them so we can come up with a consistent international estimate of the carbon budget using all of those assets together in an international framework. Right now, that framework doesn't exist, but if I understand what you're saying, we need to build one.
okay, thank you very much, Kevin. And I'm aware that there are some JAXA people in the audience, and people from ESA spoke, and people from the guy from NASA spoke, and now it's time for JAXA. If it's okay, if someone wants to stand up. No? Ochi-san, yeah.
Yeah, thank you very much. My name is Osamu Ochi from JAXA. Actually, that we are really coordinating across the NASA, JAXA, and the European Space Agency to work together how we can integrate the system, Earth observation system. We are working for the Committee on Earth Observation Satellites, and in that committee, how we can standardize the data, how we can integrate it, different space agency data sets, even more, how we can integrate it about the data sets with in situ data, satellite data, and also some model data. This is a huge effort. We are ongoing effort, how we can realize this issue. It's not just only for the major space agency, NASA, ESA, JAXA, but also other space agencies to be involved, and also that the in situ community, as well as the model community, I think. But it's not just only the space agency effort, but I think in situ agencies and the model agency, how we can communicate together. So this is a huge issue. Thank you very much.
Thank you very much, Ochi-san. Data is really an issue, and it's a big issue also for climate modelers, and we are working on it. And so the person with a blue shirt.
Thank you. I'm Jackie Brown from CSIRO.
Yeah.
We talked a lot about what's missing from the observations and the need for more observations. Where would you put your effort in the modeling space? Is the modeling up to standard, or what would you focus on to build next to make sure the models are keeping up with the growing amount of observations?
So I didn't quite get the point. So in short, it's what is missing in the climate modeling.
Yeah. So we need uncertainty estimations and how to improve the models and the
various kind of observational data in general sense, but what we are now trying to do in the Center project is the non-CO2 greenhouse gases. That is, one of many aspects that we should work on in the future project. And Pep is raising his hand, and please go ahead.
Thanks. And hi, Jackie. I just want to make a comment that in addition to these kind of global, let's call them global sentinels and global kind of ultimately net carbon balances that we can produce, or greenhouse balances, we also need to look at regional systems I mean, what we're learning, we're just going through these many years of regional carbon cycle assessment and processes, which is something that we do in the Global Carbon Project. And CSIRO is a major a sponsor it as well, and NIES and JAXA, everyone is contributing. We realize that unless we integrate the national grid inventories, a lot of kind of regional level, highly parameterized types of models that they are, basically regionally or nationally developed. And then we utilize all these kind of satellite-based system transport modeling, that we will make just limited progress to help the nations to kind of move forward with what they are responsible. What I'm trying to say is that all these global sentinels are really good to catch things, all right? It's just whatever country such is reporting less than what we think we see. But remember that unless you really fully integrate all the information we have, on greenhouse gases, you will not be able to fully pinpoint, what the issue is that, you see some kind of a higher emission or less emission. And I think that it has been said before with this National Academy report. Kevin mentioned it very briefly at the end of his talk, where the idea is to really fully integrate the atmospheric, the biochemical modeling, the inventory data, but a lot of ancillary data that we have now. Some is global, but a lot is national, and that national data is actually, it's golden data because it's high resolution, it's well parameterized, it's well known by the scientifics from the regions. And again, that's different if we talk about, an OECD country versus if we talk about a less developing country that may not even have a national greenhouse inventory. Again, I think that Kevin mentioned this thing. So just to say, it's not all about just running these big global sentinels. These global sentinels, at some point, they need to kind of take a deep breath and just kind of zoom in with the regional community, to try to develop these regional and national systems which take advantage of all these data, but really can actually inform to ultimately one of the people we need to inform best. And that it's the governments who are ultimately the responsibles for putting in place the policies to develop the mitigation and ultimately to reach those goals on net zero emissions. Thank you.
Thank you, Pep. And Pep has mentioned some regional aspects and upgrading the data onto global scale. And I understand, Saigusa-san, you have been working on regional observation for a long time, and I expect you have something to say now. If yes.
Yes, I think the global collaboration is definitely important. And for example, in Asian Pacific, first of all, there is still some observational gaps, special gaps in the for example, in the Siberia or Central Asia or on the ocean. And we have to make a kind of observation systems, first of all, in the national scale and in the Asian scale and Asia Oceania scale. So that is one point. And the satellite and the airplane observation may cover larger scale, but still we have to have high quality ground-based long-term data. So in this case, we have to have a kind of monitoring network. So we of course have some regional networks, but we have to make this network more, how can I say, integrated one or operational one to gather data stably. That's all.
Thank you, Saigusa-san. And Kevin, you also have some comments on that.
Yeah, I just wanted to follow up on the colleague from, what's your name again? Jenny? Jackie. Okay, so one area that I think is a frontier in terms of modeling let's take the case of Australia, 2020. We just lost a massive amount of emissions from biomass burning. If I'm looking at 2030, which is a watershed moment, right, a marker, how well can we predict what the emissions and how the climate will change in Australia by 2030? Most of our modeling techniques are built either on the very far time frame, 2100, 50 years, 100 years from now, or the very short, tomorrow, maybe a week, maybe sub-seasonal. But this range at the global stock take scales, 3 to 5 years, how predictable is that? Will you recover that carbon cycle by that time? Given the changes we understand in the climate modeling, can we have any predictive skill about how the carbon balance will go given a pathway? I think this is something that's not yet been really addressed because it's in this middle ground between long and short. And I think it's a frontier for modeling and a data simulation to address that time scale.
Thank you, Kevin. Biomass burning or wildfire they are something that we are trying to incorporate into the climate model or our system modeling. I think Kevin has mentioned the chemical atmospheric chemical observation for detecting biomass burning, and I understand Kanaya-san is expert on the atmospheric chemistry. So if you have something to say about this, Kanaya-san.
Yeah, about the air pollution associated with the biomass burning and other processes are quite important. And maybe from a bit different aspect, but I may make a strength that not only the regional but also even the very small scale emissions, as Kevin mentioned, the single plumes from 2 countries today. But those kind of the emissions from the cities or even the district level would be very important to look at, particularly for the CO2 as well as for the short-lived climate forces like ozone. Ozone is produced from the methane oxidation, and methane lifetime is controlled by the atmospheric chemistry.
Kanaya-san, could you speak a bit louder? Sorry.
Okay, sorry. So the atmospheric chemistry is important aspect. Particularly. So do you hear me? Well,
yes, much better. Yes.
A bit better. Okay. So the related to biomass burning, the atmospheric chemistry like a black carbon and other species may warm the atmosphere in addition to the GHGs, and also the ozone can be produced from the oxidation of the non-methane hydrocarbon with NOx, and ozone is also is an air pollutant as well as a third most important greenhouse gases as well. So the controlling methane may reduce the ozone as well. So the methane lifetime is limited by the OH radical that is determined by the atmospheric chemistry. So they are pretty much complicated and related, but by measuring them all together, we can understand the system a bit more better. And particularly, the emissions from the small sources, as Kevin mentioned today, the 2 plumes from even the plume from the industries are measurable even from satellite or some other instruments. So looking down to that scale is also important to increase the people's awareness as well, I thought. And people awareness will thereby increase and will give feedback to accelerated emission reduction is quite important. And maybe as related to the Shobakawa-san's talk, as a city scale emissions and potential reduction. Thanks.
Thank you very much, Kanaya-san. And people are starting to ask questions online, and I'll be picking up some of them. And there is a question from Hiroshi Tanimoto-san from NIES and to Shobakawa. And I will just read it up. Shobakawa, you highlighted in the last slide the needs of cooperation in Asia and Oceania. I generally agree, and I wonder what you think or feel on who should cooperate more. What's missing in the current landscape, you think? Scientific cooperation, scientists and policymakers, public and private sectors in East Asia, Southeast Asia, or South Asia. Of course, all of those. But if you pick up just one, what is it?
Yeah, I think if you look at some of the emission numbers coming out globally, you see that in terms of if you look at some of the emission numbers, you see that coming out from Asia and also the developed Asia. When I say developed Asia, usually the Japan, Korea, Australia, these are a part of the oceanic countries. There, there's a lot of thrust there from the developed countryside. And also, if you look at the per capita emission, the Australia comes to the very, very high level. So of course we need a cooperation globally. There is no doubt. But within Asia, I think we have been in most of the Asian discussion, we have not been discussing about oceanic countries. So Asia and oceanic countries can also have lots of collaborative arrangement, and particularly Australia, and that part. But definitely we need a global cooperation. Of course, there is no doubt. Then if I look at Asia in particular, I think a lot of new emissions are happening in Asia. And also if you look from the urbanization perspective, a lot of urbanization happening in Asia, a lot of infrastructures are going to build in Asia. So that is in quite a frontline situation. But of course, globally speaking, we have two different trajectory of actions needed. One for developed countries to go more towards reducing per capita emission and going down. At the same time, for developed countries not to increase emission and also go towards a bit more greener development path. So we have to find that so-called sustainability corridor to really move forward. But definitely we need a global action, definitely. But in that part of the world, oceanic countries is a little bit not really integrated in the Asian discussion.
Thank you very much, Tsukuba-san. And we are discussing very much about international cooperation, and I hope this ignites the international cooperation further. And sorry, I have another question from the online audience, and maybe this is to Kanaya-san because it's HFC gases. According to the project drawdown, it is suggested that decrease of F gas is the most important and effective, although I think that the fraction of F gas, such as ACFC, among GHG is very tiny. Does anybody has any comments about this? And perhaps Kanaya-san can give a general answer to that.
Okay. Although, yeah, I'm sorry, I'm not very much aware of this drawdown project, but yes, you were right that F-gas contribution to the warming degree is as described in the IPCC report, and it is not very big, but of course the sustainable, it's increasing, and control of the HFC gases are quite important to the Kigali Amendment. Is also effective, but we need to follow that quite strictly. That's my answer. Thanks.
Thank you very much, Kanaya-san. And maybe the question from ESA guys. First, this is the last question according to time.
Yeah, thanks again, Frank Martin Seifert from the European Space Agency. I would like to come back to point what Nobuko was making, that there are still gaps in the in situ network in Asia. Well, we are here at COP27 on the African continent. How are the gaps of in situ measurements here in Africa, and who is taking care of it? Are there any efforts to improve the in situ measurements here in Africa, thinking about what I said before, a global solution?
Thank you very much for the question. Perhaps it's a question for Saigusa-san, but it's not easy for her to answer. But if you have something to say, then please go ahead. Saigusa-san.
Okay, so I will quickly answer, and I'd like to ask Pep also to answer to this question. And from my side, one of the most important thing is that most of the in situ observation, many of the observation in the world is based on the is supported by research fund. I mean, 3 year or with the period of 3 year or 5 year or so, and but we still have long-term monitoring for 10 years or 20 years to achieve to answer the question of this kind of to respond global stocktake. So from my side, one of the things we have to do is to bring such kind of research level observations into a kind of national or international long-term activities with operational systems, with some operational systems with some long-term financial support. That's all.
Thank you very much, Saigusa-san. And if Peppo or Patra have anything to say.
I can just very quickly add that if the question is about deployment of ground observations to validate some of these global products, or just going to be able to develop the proper models, there's very little going on. I think that we in the GCP, we made a big effort over the years to encourage teams to develop, what we do, the African carbon budget and greenhouse budgets. We have actually put a whole team now working on this. They'll deliver by the end of this year. But the important thing is that outside of really key areas, which are, by the way, hotspots, investment mostly from Europe, there's very little going on. And I do want to highlight that there is now a lot of emphasis, particularly from the UK, on the big peatlands of the tropical regions, particularly the Democratic Republic of Congo, something that we know it's a huge hotspot, potentially an important feedback. And there's also a lot of emphasis as well on methane from lakes, freshwater lakes across the continent, because the extent of the continent, they're quite relevant and we know very little. Other than that, there's very little going on. And I think that what's important is really to develop these partnerships between, the regional groups with some capability and others, richer nations investments, where we can then try to develop groups, modeling capability, and ultimately the products that, we need to develop, like these larger scale greenhouse gas budgets.
Okay, thanks. And Patra?
I am not a measurement person, but sometimes we do collaborate with people who want to make measurements. For example, we have one stations making greenhouse gas measurements by sampling air from Bangladesh. So yeah, it's a project we started with APN support in 2012, and that is still running like the NIES support, and that is we have 10 years of data. But these kind of success are not very common, because just like I was mentioning that the project finishes in 3 years, but then who takes over that? But if there is a strategically designed network, if there is a strategically funded project, and what I see in this space, because I see NASA here, I see JAXA here, and I see the European Space Agency here. From outsider, I think that the space agencies are rich, but they need data for validation. They need that down truth for validation. Satellite instrument, we have CO2 measurements, for example, by satellites, or methane, but the very little ground truthing for the upward looking FTS measurements from Africa or Asia. So, I mean, that is one thing I would think the space agency could do or encourage, that you prepare a common network which can be of common interest and deploy in a strategically located sites. That could be one of the way forward, as I see it at the moment, for the measurements into improving measurement data gaps. I think with that, I will stop with my quick comments.
Okay, thank you very much. And and we are coming to an end of the session according to the timetable. And I would like to again thank all the speakers and panelists. So please give them a big hand that they deserve. And I also thank the audience for a vigorous question and discussion. And well, to be honest, we prepared some sort of discussion scenario in case there are no questions, but that was in vain, very fortunately. Yeah. So I thank again the audience, and this concludes the session. Thank you very much. Have a nice afternoon.
Thank you.